Our group is going to be talking about the Boyer-Moore algorithm. The Boyer-Moore algorithm is a pattern searching algorithm whose main goal is to find a pattern between two input strings. For example, let's say we have string 1 to be 1122 and string 2 to be 11. The pattern in this case is 11. So when we run the algorithm, we will return index 0 because in the string 1122, the pattern begins at index 0. The way the algorithm is able to find the pattern is through a combination of pre-processing the input strings, as well as the bad character rule and the good suffix rule, which we will take a deeper look at later in the presentation. This algorithm is very prominent in our lives. We use it when we're running spell checkers, spam filters, search engines, and even in plagiarism detection.
Now let's discuss the history of the algorithm. So it was first developed by Robert S. Boyer and J. Strother Moore, and the algorithm was first presented in the 1977 paper, A Fast String Searching Algorithm. But the original paper was actually focused on static tables for computing pattern shifts, but it didn't provide much of an explanation how to produce them. But the algorithm for producing these tables, later known as the Boyer-Moore algorithm, was published in a follow-up paper. Later in the 1980s, a Boyer-Moore horsepool algorithm was developed, and it was basically a simplification of the original Boyer-Moore algorithm, and it was just another method for finding substrings in strings.
Now I'm going to talk about the pros and cons of the Boyer-Moore algorithm. The advantage of Boyer-Moore is that it can achieve sublinear running time by skipping characters according to bad character rule and good suffix shift, which were mentioned before in the intro, as we don't necessarily have to read every single character of the text. Specifically, the bad character rule can be used to skip over huge regions of the input string in the event of a mismatch. There are two disadvantages of the algorithm. The first one is that it needs additional space usage in order to store two tables that are created by the two main approaches. Another disadvantage is it performs badly on short strings. The reason is that the algorithm works by creating jump tables. It takes time for calculating tables and looping itself. For example, there's a string with only 4 distinct letters that creates a jump table with a maximum of 3 shifts per mismatch. Therefore, we can know that the naive search algorithm is better than Boyer-Moore in this condition, since there are very little operations inside the naive search algorithm's loop, so the loop runs fast.
So now let's talk about how the algorithm runs. The Boyer-Moore algorithm starts off by pre-processing the pattern by storing all of its possible mismatches in the lookup table. This is done so that when a mismatch is found, the algorithm knows exactly how many characters to shift right to create a new alignment with that mismatch character. The alignments are ordered from left to right, just like most other string matching algorithms. However, the character comparisons are actually ordered from right to left. This is because ordering from right to left allows us to skip a substring of mismatch alignments. The algorithm also consists of two rules, the bad character rule and good suffix rule. The bad character rule states that if a character is mismatched, we have two choices. We either skip our pattern past that character, or we align our pattern with that mismatch character if the mismatch possibility is stored in our lookup table. The good suffix rule is a bit different. Instead of aligning individual characters, it uses the pattern's matched substring to skip alignments until the substring is matched again. When new characters of the pattern are matched, we prepend the characters to the matched substring. This process is repeated until either the entire pattern is matched or we conclude that the text doesn't contain our pattern. The bad character rule and good suffix rule can be used together, but they can also be used independently. For the sake of clarity, we'll show examples for both rules individually.
In this example, I'll be talking about the bad character heuristic of the Boyer-Moore algorithm. The string that we'll be looking for is piazza, and we'll be looking for this string inside the string, did you ask about the pizza on piazza? First, we align the strings at the very beginning, and then look at the rightmost character of the word that we're looking for. You see that the O and the A are lined up, however they do not match, and we do not see an O in piazza, so we shift the whole word's length. The A and the space character line up, and there's no space character in piazza, so we shift another whole word length. And again, A lines up with the space, and there's no space in piazza, so we shift another word's length. Here we see that the I and the A line up, and they do not match. However, we do have an I within the word that we're looking for. So we shift however many characters in order to get the I's lined up. And in this case, it would be 4 characters. And here we see that the I line up and the P line up. However, at the very end, we see that the A and the space are lined up. However, they do not match, and we have no space within our character, within the word we're looking for. So we have to shift the whole word's length. Here we see that A lines up, and looking at the next character over, I and the Z line up. However, they do not match. So again, we look for the I within our word, and we see that we have an I, and we'd have to shift 3 characters over in order to have them line up. So when we shift 3 characters over, we see that the word lines up with the word in the string, and this is where we would find our word. In our next example, we'll be looking at the good suffix heuristic. The word that we've been looking for is banana in the string. Did you get the bandana in Montana or banana? So again, we line up the strings initially on the left-hand side, and then we look at the rightmost character, and we see that the O and the A line up. However, we do not have an O within our word that we're looking for, so we have to shift the whole word's length. When shifting whole word's length, A and the space character line up, and there's no space within banana, so we shift another whole word's length. We see that A lines up with A in banana, and then looking at the next character over, B and N does not line up. So we would have to look for another instance of A that lines up within our word, and that would be shifting 2 characters over. So when shifting 2 characters over, looking at the rightmost character in our word, the A and the D line up, however they do not match. And we do not have a D within our word that we're looking for, so we would have to shift the whole word's length again. The N and the A does not line up, so we would have to shift another whole word's length. Here the A lines up in Montana, and the T and the N line up, however they do not match. So we have to look for another instance where an A exists within our word that we're looking for, and this would mean we have to shift the word 2 characters over. Here the A, N, and A all line up, and looking at the next character, the T and the N line up, however they do not match. So we have to look for another substring of A and A that lines up with A and A within our word, and this would be that middle chunk. In order to have that middle chunk line up with the ending A and A, we have to shift the word by 2 characters, and we see that the O and the A is lined up, and we have no O within our word that we're looking at, so we have to shift the whole word's length. Here the A is lined up with the first A in banana here, and we looking at the next character, B and N line up, however they do not match, and we have to look in there for another instance of A to shift, and so we shift 2 characters over, and we see that the A and A line up again, and looking at the next character, the B and an N does not line up again, so we have to look for another substring where A and A matches again, and this would happen when shifting the word 2 characters over. And so when shifting 2 characters over, we see that banana lines up with the banana in the sentence, and this would signify that we have found our word.
The runtime of the Boyer-Moore algorithm consists of two parts, pre-processing and matching. So the pre-processing part of the algorithm simply means that we are pre-calculating skips for all possible mismatch scenarios. Now, the algorithm uses the two different methods to calculate matches, and that's why and these two different methods give it the runtime that we see here. So the first one is the bad character heuristic, and the other one is a good suffix heuristic. Let's see an example. So for the bad character heuristic, let's say we have a mismatch. So D and X obviously don't match. So using the bad character heuristic, we would move this pattern until this bad character finds its match. Now, why is it efficient? It is because we can skip several characters until we find the match, and we don't do that in the brute force methods of searching, right? In a brute force method, we would check every character, but here, if we know it doesn't have a match, we can skip those. So that's one of the contributions to the runtime. Now, for the good suffix heuristic or the good suffix rule, the idea is that if we already found a match for, say, two characters, but the third one still doesn't match, our goal is to find a match for this character without ruining the match for these two characters. So again, if we already found a match and we still have one mismatch, the goal is to fix this without ruining what already works. So let's go back. Now, it is important to note that for the Boyer-Moore algorithm, we start matching from the last character, so from the end of the string. And the worst case happens when all of the characters in the original text we're searching and the pattern are exactly the same. So let's say you have a pattern is a string of 5 capital B's and your text is made up of 1,000 capital B's as well. So that would give you the worst case. Now, the best case would be the exact opposite, and that would be if your pattern and your text are completely different. So that's for the runtime of the algorithm.
So just to recap what we've gone over the Boyer-Moore algorithm, which is a pattern searching algorithm. It consists of two main processes, which is the good suffix rule and the bad character rule. And the runtime for this algorithm, assuming that pre-processing has already been complete, is big O of M times N. These are our questions regarding our presentation, and I hope you guys learned something and had fun listening. Thank you.